What's up, guys, and welcome to this video on the 2018 supplementary exam. We're doing question 2, kinematics and gravitational fields. Okay, so let's get straight into the question. Okay, so the question says, a ball on a distant planet is dropped from a certain height. The velocity time graph represents the motion as it bounces vertically on a solid floor. The time of the bounce is negligible. The planet has no atmosphere, so there's zero air resistance. Okay, cool stuff. No air resistance. Okay, so this is the velocity time graph, which is given to us. So let's just understand what's happening. So the ball is being dropped. So we can say that as the ball is being dropped, the velocity is increasing, as we can see here. So we can also say that down is therefore the positive direction here. Okay, so this graph, if the velocity, this velocity is a downward velocity, and this would be an upwards velocity, in the upwards direction and downwards direction. Okay, cool. So question 2.1, nice freebie definition. Acceleration is the rate of change of velocity. Okay, velocity. Okay, cool stuff. That also translates to the gradient of a graph, right? Okay, cool. Next, 2.2, calculate the magnitude of the acceleration of the ball on this planet. Okay, so here the acceleration is equal to our gradient, which is equal to our change in y over change in x. Okay, so now we need to choose 2 points. Okay, I'm going to choose this point here and the origin, because that makes life a little bit easier. Okay, so our change in y is going to be, I'm going to label this a, this point b, so it's going to be a, or y of a, which is 3,2 minus 0 over the x value, which is 0.5 minus 0, and so the acceleration is given as 6,4, and the has units of meters per second squared. Okay, and that's our answer. And 2 marks and 3 marks. Okay. Question 2.3. Okay. Calculate the height from which the ball was dropped. Okay, so how are we going to do this? The easiest way to do this question would to just use okay, so this is where this point here, if you look at that point there, that's where the ball hits the ground. Okay, here it starts leaving the ground. Okay, so that means the height from which the height would be the area under this graph right here. Okay, so if we want to get the height, we can say that the height is equal to the area, which is equal to a half times the base times the perpendicular height. Okay, and we know that the base is 0.5 and we know the height is 3.2, and so the distance or the height is 0.8 meters. Okay, cool stuff. Okay, then it says 2.4, draw a labeled free body diagram showing the forces acting on the ball at 0.7 seconds. Okay, so where is 0.7 seconds? It's probably somewhere here. 0.7 seconds. Okay, so what forces are acting on? Okay, so this is where the ball has now hit the ground, it's left the ground, and let's say at 0.5 seconds it's moving upwards again. Okay, so there's no external forces acting on the body besides gravity, right? And we're gonna label this weight. Okay, so that's basically, you can say that you've got your mass and it's got a weight. Basically, that's all there is. There's no other forces acting, and that's your free body diagram, and you get your 2 marks. Cool stuff. Okay, 2.5. Okay, so the question here is the collision with the floor elastic or inelastic? Okay, so how are we going to determine whether it is elastic or inelastic? Okay, so we know the area under this part of the graph here was, let's see, what do we say? It was 0.8 meters. Okay, if we wanted to calculate the area under the next part of the graph, which is this part right here, it would be a half times the base, which is 0.9 minus 0.5, times the height, right, perpendicular height, and that gives us a value of, let's see, gives us a value of let's say the area here is equal to 0.2512 meters. Okay, so clearly the ball doesn't bounce up as high as it, or doesn't reach the height, so it's actually lost energy. So it's definitely an inelastic. So you can say inelastic collision, and the reason we can say is the ball doesn't bounce back to the same height. Okay, also we could have noticed that the velocity here is basically it doesn't bounce back to the same height, so it is an inelastic collision. Okay, so we get our 2 marks there as well. Okay, question 2.6. State the magnitude of the velocity with which the ball hits the ground at 1.3 seconds. Okay, so in this situation, what we have is basically we're looking for this value right here. Okay, and remember we're dealing with constant acceleration, and there's no air resistance as well. So if we remember our free falling properties of free fall, is that this velocity here is going to be exactly, because it's going from, it's off, so here's the first bounce, then it's going exactly back to the second bounce, or the bottom of the second bounce here. So this velocity is going to be exactly the same as that velocity, which is 2.56. Yeah. So we can write the answer as being question 2.6. The answer is 2.56 meters per second. Okay. Yeah. So there we go. So this was when it's left, and then when it hits the floor again, it's going to have the exact same velocity as which it left, because it's body in free fall. Okay, then it says 2.7 on the same, okay, so on a set of axes, we want the position time graph of the motion from 0. Okay, so I basically actually did that here, but I will do it formally as well. So 2.7, we have the following set of axes. Okay, so it wants position, which would be in meters, and then it wants time, which would be in seconds. Okay, so it's initially let go from a certain height, right? So it's going to start up quite high, and we actually know this height, but it doesn't ask for values. Okay, then what happens? It goes down, and then it goes down, and hits the ground. Then it leaves the ground. Okay, so we're right here, we're leaving the ground now, and we know that it doesn't reach the same height, but okay, and then what happens is, so that's this point right here, it's its maximum, or the turning point, and now it starts going down until it hits the floor right there. Okay, and let's see, so we know that this is 0 seconds, we know this takes place at 50, the turning point is at 90, and this is at 1,3, 1, 0, 0,5, 0, 0,9, and 1,3 seconds. Okay, cool stuff. And that's question 2.7. And now we're working on question 2.8. Okay, so the Earth has a mass of m and a radius r. The distant planet has the same mass, quite important, as the Earth, but a different radius. Okay, use the answer from question 2.2, this question right here, to calculate the radius of the planet in terms of r. So r is the radius of the Earth. Okay, so I'm going to do it next to question 2.2 because we're using question 2.2. Okay, so question 2.8. Okay, so the governing equation that we're going to be using is the equation for gravity of a planet, which is G equals the gravitational constant g times the mass of the planet times r squared. Okay, so if we did this for the Earth, g of the Earth, okay, or let's just say g of the Earth is equal to g m r squared, right? But if we do it for g of the planet, we know it's going to be g. The m's are the same, but the planet has a different radius. So we're going to have to say it's the radius of the planet squared. Okay, so now both of these things, g times m, because they have the same mass and g is a constant, the two circled in red are equal, right? So what we can do is we can get each equation in terms of gm and then, so let's go, gm is equal to gravitational force of the Earth, or acceleration of the Earth, times the radius of the Earth squared, and gm is equal to gp times rp squared. Okay, and now we can equate these two. So we can, I'm going to substitute. Okay, we know the force of gravity of the Earth is 9.1 r, or 9.8 r squared is equal to, and we know this is 6.4, gp is equal to 6.4, 6.4 radius of the planet squared. Okay, so now we just need to divide both sides by 6.4 and then square root both sides. Okay, and so we get, at the end, we get radius of the planet is going to be equal to 1.24 times the radius of the Earth. Okay, and that's what the question asks us for. It asks us for the radius of the planet in terms of r, and we have the radius of the planet in terms of r. Okay, cool stuff. So not too difficult. Yeah. Okay, so that's basically that question. And yeah, that's going to be the end of the video, and we'll do the next question next time. Okay, thanks for watching, guys.